Good morning, everyone. Let's wait a few more minutes and we can start. Today, we just want to be reviewing uh, what we learned so far in this course because we are wrapping up chapter number 11 or chapter number 1 and 2 from your open textbooks. All right, are you guys able to see a black color screen?
Yes.
All right, so let's start it. In this chapter so far, or in this course, we learned a bunch of different things, but mostly we talk about vector geometry. Right. So really what we learn here is how to draw vectors. Right? And also, and when I say how to draw vectors, we learn two things: how to get the magnitude, and then direction. Remember I told you if you draw a vector like this and you draw a vector like this, there is a big difference. The size is different and maybe the direction is different. Okay. In real life, when we draw vectors by hand, usually you don't care about how big is the vector you are drawing. But in the field of engineering, the vector size, magnitude right? So rather than you say somebody asking you, draw a 5 meter long vector. How are you gonna draw? You're gonna draw a vector roughly. You say this is vector. Another person says, hey, you know what? This is vector. Another person say, you know what? This is a vector. All three are correct because all three just drawing vector as per their judgment. But everybody has to give me the size of the vector, which is this magnitude, whatever is there, the 5 meter I just mentioned, give the example. But also you have to give me the direction, so you have to give me the theta. So all these 5 people or 3 people who participate in this exercise, they're supposed to give me the same number. And that's exactly what we're learning here. Okay. Students usually confuse about another topic which is going to come right after the midterm exam, and that is the main part of vector, uh, uh, multivariable calculus, which is called vector calculus. Okay. So vector calculus and vector geometry are two different topics. Here, we are not talking about size of the vector. We are talking about whatever. This vector b. I'm going to take this vector b and I'm draw a line, and I'm going to take this vector along the line. So really what I'm going to do, I'm going to take all these 5 yellows, small vector, and take the integration from point A to B. So I'm going to write in here B to A, and then I'm going to integrate this field. I'm going to call it vector calculus. Rather than I can call vector in that time, I'm going to call it vector field. It means vector is not just one vector. Here's a vector is one vector. Over there, when we talk about vector calculus, we do not have one vector. We have a line, and at that line have a bunch of unlimited vectors, right? Just like the wind is blowing, and how are you going to draw the wind is blowing? But does the wind can be feel? Yes, wind can be feel. So it means wind is a velocity, and velocity have a vector. So what you do, you have a wind is blowing. All you can do, take one line of the wind, and then start making these white color small vector, and these small vectors called vector field, and we're going to use that vector field in vector calculus. So let's go back what we're learning in vector geometry, and that's our goal, is to just get some overview of what we're learning so far in this course. So the first thing we learn about here is vector in plane. Okay, vector in plane, we're learning a bunch of different things. The most important thing we learn in vector in plane is, if I gave you two vectors, points, right? The only thing is here we're learning is size of the vector, first thing. And the size of the vector, if I gave you 2 point x1, y1, x2, y2, I'm going to call this point R, this point B. And what we're learning is PQ distances x2 minus x1 squared plus y2 minus y1 squared. If someone gave you some point, for example, let's suppose that P is given 2, 3, cube R is given 4, 8, and you want to know P R, we use the 2 mark, and I'm going to draw a little arrow, it means it's a vector. Also, I'm saying PR, so I should be drawing a vector arrowhead here. And what I'm going to do, I'm going to just substitute the values, 4 minus 2 squared plus 8 minus 3 squared. Okay. Another thing we're learning, we can get the answer, whatever answer we got here, maybe is 2 squared plus 5 is square. So it's going to be 4 plus 25, so it's going to be 29, and square root, right? Another thing is that if you want to see, we are doing the magnitude, so really it doesn't matter. We are doing the magnitude, so really doesn't matter. You go from P to R or R to P. So if you want to do R to P, you can do it. You can also do the same thing. And the answer should be 29, right? It doesn't matter really because the way you're doing it. This is square cancelling out the negative sign, if there is any. Now afterward, what we're learning is vector can also be written in 3D form, right? Vector can also be written in a 3D form. And if I have the same situation for three-dimensional, I can just extend my formula for 3D, and I'm going to start writing this formula p cubed. Let's suppose I have a z coordinate here, 1, 2. I'm going to be just extend my formula for the third coordinate. And that's exactly going to be doing the same thing. Right. Then we learn vector in a unit vector form. Vector in a unit vector form. But before we do this, we talk about what is unit vector, right? So the unit vector is a vector has one unit magnitude. Okay, one unit could be 1 unit means 1 meter, 1 millimeter, 1 mile, whatever. I say 1 unit means is 1. Now, the way it works is here is unit vector is you only care about direction. The unit vector purpose is to only get the direction. And what does that mean? It's saying today we have the wind is blowing, so there's a tree here, and and the wind is blowing this direction, and the tree is basically because the wind is just tilting on the other side, is blowing on the other side, and the wind is blowing and pushing the tree on one way or the other. Now our goal is to find the direction of the wind. I don't care how strong is the wind, maybe 180 miles per hour, right? I don't care about 180 miles per hour. I just want to know where the wind is blowing. So what I'm going to do, simple. How can I get the vector? Unit vector, I take the vector and divide it by vector magnitude. It's a very important concept. So when I say magnitude, look into that. Magnitude means just the size. Vector means size plus direction. It's not really a mathematical plus or arithmetic plus. It's basically size and direction. I would say size and direction. Size and direction. So what's happened when you do this kind of math? Really, you can cancel this size to this size. And what is left over? Only direction. And what is left over when you divide is only 1. And that is why we call unit vector having a 1 unit size. Direction is there, but there is a size. Okay. I'm going to complete this before I go back to this slide and talk about unit vector form. So let's complete this one. We're also learning about unit vector. So let's suppose I give you a vector P, and I give you the vector 5, I, comma, 3j, comma, 7k. I use this comma if it's given right this. I don't have a parenthesis. I also told you if I don't have those parentheses, like those one, if I have those parentheses, I'm fine, right? But if I'm not writing the parentheses, I should be doing it plus sign. So what I'm gonna do, I'm gonna get the magnitude of vector b. While we are in this topic, I can tell you one more thing is we discuss is that some of the books they say only single mod, just like is mentioned here. But in your book or what we're doing so far in this course, we're doing this. So sometimes you say single, sometimes you say double. The way it works is that it's not really um, too important which one you follow. You can do one or two. But in this book, you says if it's a B, you use double, like one vector. But if it's a B cross A, so after you getting a product, then they use single. That's how it works in this book. Yep. So this magnitude have two different kind of notations. Make sure you note with them. And I'm going to be just doing the same thing. So it's going to be 25 plus 9 plus 49. What would be the answer for this? Please put your answer in a chat. Square root 83. Okay, don't worry about too much to simplify that number. We just want to know and overview and refresh our memories how the unit vector works. So what I'm going to do, since unit vector is another vector, see, b is long vector. I take the vector b and divide it by magnitude. I am expecting there is a new vector will born, and the new vector, which a newborn vector will be, is going to be little tiny vector. It has one unit magnitude. Direction is same, but the vector size is different, so I could not use b. I supposed to be using maybe says u is a unit vector. Maybe I can just name this vector u. This big vector is b. So u is a unit vector. So what I'm going to do, I'm going to take the vector b, which is 5i plus 3j plus 7k divided by its own magnitude, and I'm going to get this. Just like I mentioned, we're going to skip today some math part, so we use the time, most of the time, to review the concept. Yeah, this is my unit vector. I also already told you, you can also write the unit vector. Now the thing is, let's go back here in a unit vector form, vector in a unit vector form. So what I'm going to do, I'm going to take another vector here and just draw here. So this is y, this is x, this is z. I'm going to draw a vector, and I'm going to make one component here, one component here, one component here. Let's change the color real quick and then talk about this is a component in maybe this vector called f. I'm going to call fx, and this one is fy, this one is fz. So really I have a f vector, then fx plus fy plus fc. I can also write this f vector in a parenthesis vector form. So I can say it's fx comma fy comma fc. Okay. Now I also want to know that which one is what, right? Which one is what? So basically I give you three component. You want to know how much is going. So I'm going to say is fx equals to 10, fy equals to 5, fz equals to 3. So you're going to say, you know what? That's right. Fx equals to 5. Oh, sorry, 10, comma. Fy equals to 5, comma. f z equals to 3. Parenthesis close, this is vector. But since at 10, 5, 3 are in the direction of standard, I use the word standard direction. They are not a random direction. Like here, it's a random direction. Like this U is a random direction. I don't know where the B is. Yeah, I don't know where the B is. So U. So now you notice one thing. This U is in the direction of B. This U is not in the direction of I, J, or K. So go back. If I want these little component, these are the component, one component, another component, another component. This is X, Y, Z. So for those standard direction, I use the word standard direction. I can just punching the different kind of symbol I, J, K. It is very useful to telling me yes vectors go 10 in I, 5 in J, 3 in K. And if I give you another vector, let's suppose if I gave you another vector here, vector K, and is equal to 2I plus 3J plus 4K. And if I'm asking you adding this F plus K, can you add them? When you want to add them, what you're going to do? You're going to be taking this I part, add them together will be 12I plus this 5 part, this 3 part, because both are in J, so it's going to be 8J plus this 3 and 4 is going to be 7K. And that's why the IJK is have some importance. Then you want to add and subtract the vector. Okay. Okay. Then moving forward, we also talk about direction cosine, right? We also talk about direction cosine, and direction cosine is pretty straightforward. I'm just going to be writing real quick here. Every vector is given, right? I want the direction from there, I want direction from here, I want a direction from there. And I told you this is a direction cosine. And it's going to be cos alpha, cos beta, cos gamma. These are the formulas given, whatever the axis. And then you can divide by the magnitude, right? Whatever the magnitude we have on the vector. So you can do this part. It's not important, just moving forward. Okay, then we talk about another topic. It's called dot product, cross product. Okay, dot product means when I want to have a vector, whatever is vector, and then b vector is ijk or any form, this vector, I want to multiply them. So what you're going to do, you take the I component, multiply the I component, the j component, multiply the j component, and k component, multiply the k component, you get the answer. And you can also write a dot b, and then a magnitude, b magnitude, cosine theta. And when you solve this guy, you're going to get the answer. Your answer should be a scalar quantity. It means no direction. Direction is not a concern. You want to know how much. And really, what is the dot product means? The dot product have two methods. This is method number 2. This is method number 1. You multiply, and just I'm going to be writing a little bit better here. You're going to be writing like a dot b is, ax dot bx I plus ay dot by j plus az dot bck. This is method number 1. Method number 2, you can apply one or the other based on the information it's given. If it's not given, if this is not talking about the angle, if there is no information giving about the angle, then you're supposed to be using the first method. And if they're talking about the angle, then you are forced to use method B or 2. Really, what is a dot product? Dot product means if I have two vector, vector B, vector A. In these two things, I want to know how much B shadow projection in A. So what I'm going to do, I'm going to split the vector B. So I'm going to only taking this portion of B and multiply this portion to A. And really what I'm applying this called BX. So really what I'm doing, I'm multiplying A to the BX. And if you know that, what is the value of BX? BX equals to B cos theta. And that's why this formula generated. This is exactly what this formula. You're just trying to make a multiplication of the two. So you multiply like this. But if you have vector A like this and vector B like this, in this case, you're supposed to be writing AX dot B, right? That's what you want. If that's the problem is saying, if you have A dot this scenario when A is an angle and B is a different direction, that's what you can do this way. Okay. Now, dot product is relatively simple, and cross product is a little bit tricky. In cross product, I want to multiply two vector. So I have size, magnitude, and then I also need fraction. So the point is that if A is going this way, B is going this way, I want to know how different they are. In cross product, I want to know how different they are. In dot product, I want to know how similar or same direction the vector are. In cross product, I want to know how different direction the two vectors are. So cross product is must be happy if two vectors are making 90-degree angle. Dot product is must be happy if two vectors A and B, like A is here and B is here. Must be very happy because both are in the same direction, 0-degree angle. So when you multiply them, this cos 0 will be 1. So you just multiply and getting 1. But if B start changing or A start changing, this whole 1 start reducing, less than 1, maybe 0.9, 0.8, and if two vectors are 90-degree apart, there's nothing similar left over, so this cos 90 will be equal to 0. So this whole product is equal to 0. So two vectors are 90-degree apart, their dot product is 0. Okay. Now the thing is very important here. If two vectors are here, if I'm going to be drawing into 3D, that will be much easier to understand. So let's suppose I have a 3D axis, and then there's a y, there's x, there's a z, and I have a vector A here, vector B here. I just told you a few minutes ago, these a best case scenario when vector A and B are 90-degree apart, cross product is happy. So cross product is going to be A cross B equal to AB sine theta, right? And you're going to be putting a little n, which is a unit vector. This is a unit vector direction, or you can call the direction of the cross product. Let me talk about this one. So now the thing is, A and B, two vectors, A is 5, vector B is 3, whatever. You multiply them, this 15 come to the answer, 15. Now this 15 is the magnitude. The argument will be where this 15 goes. Goes towards A, goes towards B. So we are making another rule called right hand rule, or some people call it right hand law. And what you do, you just take your thumb, index finger, and then middle finger is like that, and then so that's your thumb. So what you do, you just take your three fingers. This is A direction, this is B direction, and the thumb is actually your resultant. If I apply this analogy here, right, my finger is here, My middle finger is here. My thumb is on the top. So what I'm going to do, I'm going to say is the direction of this 15 will be along z-axis. And this is basically my n. This direction is my n. So you know what I'm going to do here? I'm not going to do anything. I'm going to just write out this guy and say k. How about that? Is simple because I know z unit vector is k. So I just k. I just put a k. Okay. Now, before we wrap up this cross product, one more thing. If let's suppose my question to all of you, A and B is along this direction. If let's suppose A start moving this way, this is a new A prime. So A is moving, rotating, a little bit rotating. Now my question to first question is that A and B are still 90-degree apart. Still 90-degree apart. Put your answer in the chat. What you guys think? Or maybe ask someone. Alicia, are you there?
Yes, I'm here.
What do you think, Alicia? I move the vector A, which is right on the x-axis. I just rotate a little bit. Still on the ground. Still on the ground, like a floor. Do you think the A and B right now, the A prime and B, still 90-degree?
No.
No. Okay, so A and B is not 90-degree. So what we're gonna do? We're gonna make this thing. You try to close your finger. So you bring your index finger here, but still have an angle. So my question is to Alicia for you. If I move A from A to A prime by using your right hand, where your thumb is gonna be directing towards now?
It should still be up in
It
the
still should be up.
K direction.
Yeah. So earlier you have thumb. Now your finger is a little bit tilt. You know, I cannot draw the hand very well. Looks like funny, but this thing is your N or K. So really this guy is not gonna. You're further closing, you're basically making two fingers on the top of each other, right? So when you combine the two fingers, your A cross B, technically speaking, is zero, right? Because both are in the same direction. And cross product is talking about how much you are 90-degree. So mathematically you are, uh, physically you are saying is zero. Mathematically, if you say is A cross B, whatever, A, then B, then sine 90, sine zero is zero, so everything becomes zero. Okay, so this is the first, same thing like cross product, this is the first type. The second type of calculation, when you have A is given in this form and B is given in this form. And if you have two form, you want to do A cross B in a vector form is given or unit vector form is given, you maybe use the determinant rule I, J, K. You apply AX, AY, AC, BX, BY. You multiply them, and you get the answer. We already done a lot of practices on those. So please go and take a look. Let's move on to parametric equations. Then we talk about another topic called parametric equation, and then we also call symmetric. They go side by side. And really the parametric and symmetric equation is that if the equation is given of a line, like this is a line, what I'm going to do, I'm going to take this line, making two vectors here called x, y, z, maybe call 1, 1, 1. The other point I can do x, y, z, just leave them alone. In order to find a parametric equation, I must know a point on a line. And then what I'm going to do, I'm going to be just making another vector, and this vector I'm going to call V, and this vector have A, B, C. These are the component. Remember, these are the component, these are the coordinates. That's why I'm making different parentheses. And then you write in the equations like this. How this equation came from, we just talk about that. If you still have some question, please go and visit the coding. These are the vector, these are the three equations, x, y, z. You're going to be writing this. So really you see I split the equation. I split the line, right? So I split my line, right? I split my line into x, y, z. And if you still going back to the same topic, I split the line into three. If you still want the vector, you can again writing these things in a vector form. Right? These are the x, y, z, these are the component. You can write them in a vector form. Also, if you need the direction, you apply the same thing like a unit vector. The bottom line is that I say this is line, but really it's a line, but you can treat the line as a vector. The only difference is that in real life, line usually does not have any concern about direction. Line means size. When we talk about lines, lines mean size. We don't care about direction. So we did this one, and then we also writing symmetric equation. Symmetric equation means really what is that? If I have a line here, I want to put the mirror somewhere here in the center, and I want to reflect this line on the other side. So it's going to look like this. That is how you're writing the symmetric equation. And what you're eliminating this t somewhere, everywhere t, and say x minus x naught over a must be equals to y minus y naught over b, and it must be equals to z minus z naught over c. Okay. Then we talk about bunch of different thing, and the topic was surfaces in space. That's a big topic. And I told you a very detailed explanation of quadratic surfaces or quadratic equation, right? And we talk about that one. Then I gave you 6 standard form of quadratic surfaces. One is ellipsoid, and then hyperboloid of one sheet. Then I have hyperboloid of two sheet, and then so far and so on. So what exactly the standard, what's an analogy here is going to be doing? If any equation is given, let's suppose 3x squared plus 9y squared plus 9z squared equals to 81. Your goal is how to attacking this. I did a lot of, I think I'm going to be posting that lecture, just like I did earlier over the weekend. But when you watch this lecture, is going to be seeing here. What I did, I just basically closely watching my variables and their sign. And I also watching this constant. So variable, sign, and constant. And I want to make sure if this is here is 1 or if here is 0, I shortlisted which one should I pick. I go to the standard form of equation and I shortlisted whatever equation I have and whatever shape I can closely find out this one. And then what I do, I just basically taking my equation and says, you know what, just divide this equation by maybe by 9 and see what's going to happen. Or maybe if I want 1 here, I'm going to say, you know what, divide this equation by 81 and see what's going to happen. So I'm going to say 3 over 81 x squared plus 9 over 81 y squared plus 9 over 81 z squared equals to 81 over 81, and it's canceling out. So I got 1 here, which is my goal. I want a 1 here. And if I want to get the 1 here, I can just rearrange this equation. I can say this. I can further simplify this one. It's going to be 2, 7. So it's going to be this plus y squared over 9 squared plus, oh, this one not going to be, it's not going to be squared. And it's going to be z squared over 9 equals to 1. Now I know that this is a ellipsoid equation, so I'm going to be making a draw a ellipsoid, and I say, you know what, in x is going to be going to a. This is my x, so I'm going to be going a in this direction. This is my y. I'm going to be going b in this direction. Like this is my a component, this is my b component, this is my c component. If I compare with this equation, so I'm going to compare this a square, b square. So these are my square. I'm going to be just taking my square root and find out what is the value. And I'm going to be drawing a here. So it looks like a is much bigger than b and c. So I'm going to be drawing a here, b is here, and then c is here. And then I can just make my ellipsoid just like that. That's my ellipsoid. Okay, we have a last few minutes left. Let me just talk about real quick what we discuss in coordinate system, cylindrical coordinate and spherical coordinate. I'm going to combine all the topic we got up, talk about coordinate system. Coordinate system we just talk about, we have coordinate system is nothing but it's just a way of measurement. Okay, don't be confused about what is the coordinate system. It's not altogether a new science or field of science. It's basically a illusion of way of measuring things. So point is that one thing you understand, if I'm asking you in space, right, if I'm asking you about the point, you can give me the point. You can say x, y, z, right? Let's suppose this is earth and you want to shoot something. Your target is you want to shoot something. The target, you say your missile is going to be hitting this target, and you're shooting some missiles. It's going to go and hit. This is your target. It's done. Simple, right? You can use rectangular coding, which is easy. Rectangle is the most easy and accurate, or you can call Cartesian, x, y, z. The problem is that if I'm asking you taking a, this is NFL season, so the NFL ball is like, pretty much NFL ball is like this, like ellipsoid shape, right? And if I'm asking you go and then take a marker and then mark on the ball somewhere on the ball, I'm not saying any space, on the ball, mark somewhere a point here. Now what's the problem? How can I give you the coordinate from this? I cannot give it to you, this coordinate, XYZ form. That's exactly where the other two coordinate system born. When you want to mark surfaces in space. So you have three coordinate system, rectangular, then you have spherical, cylindrical, and then you have spherical. In this one, you have XYZ, Here you have r, theta, z. Here you have, and same thing if you know, if you have a pipe, like long, very long pipe, and I'm going to say, you know what, in this pipe have a contamination. You say, really? Where? You put the pipe on a microscope or maybe X-ray machine, and some contamination, maybe inside the water pipe there is a mouse or cat trap, and I want to locate that one. So I'm going to say, hey, go, and this pipe is 10 mile long. Just go and cut the pipe. The cat is stuck here inside somewhere. And this location, how are you going to get? Then you're going to be use cylindrical coordinate. So you go exactly target particular point. I mean, it's not like a guess. When you do some engineering project, you cannot guess stuff. You need a particular firm answer. So that's what your spherical coordinate comes, and spherical coordinate um, have rho, not r. Rho, I told you already difference between r and rho. Rho is using for 3D shapes, and then it's going to be theta. And there's going to be another one. Phi is my coordinate. Rectangular coordinate is usually a square where you pick the coordinate or the corner of the square. Cylindrical coordinate is just like a cylinder. You draw an arbitrary cylinder. So every time you talk about cylindrical coordinate, you're trying to make an arbitrary or imaginary cylinder or imaginary cube when you talk about rectangular, and you're talking about here. So this size is z, this size is r, and then the theta is basically how far which one you're talking about. You want to go here, you want to go here, you want to go here. So what you do, you just take a x-axis and then try to mark here. So this is, let's suppose this is a point here. I'm going to do dot 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 coming here, and you say this is a point. So that's my r, that's my point on the cylinder, and that's the angle. This angle is theta. When you talk about spherical coordinate, you do pretty much same thing. All you do, taking a point, go here, call it rho, and this taking this angle, this rho, with how far you going from x and how far you going from z in terms of angular displacement. Angular displacement means angle, right? We want to know that how we convert one or the other. So you can convert these two, rectangular to spherical. You can cylindrical to rectangular or rectangular to cylindrical. So the ratio we use here is going to be, just want to find, is going to be x equals to r cos theta, y equals to r sin theta, and tangent theta equals to y over x. If you want to go one way or the other, and z is z. And if you want to go other way around, you're going to be just saying that r here equals to square root of x squared plus y squared, right? And z, if you want to go from cylindrical to from rectangular to cylindrical or cylindrical to rectangular, these are the ratio we are using. And here the tangent theta is pretty much same thing. You're going to be using tangent theta. The other cylindrical coordinates to spherical coordinate, we cannot do that cylindrical to spherical. So what you do, you just do from rectangular to spherical. That is more doable, right? So if you, this is not a favorable or doable, right? This is not a doable job. What you have to do, you just need to find, go from here to there probably, or maybe go from here to there and then go from here to there. So the route will be just like that. If you want to go from here to there, you have to go from here to there and then go from here to there. And if you want to go from here to there, you have to go from, right? You cannot go from cylindrical to spherical. You have to go to rectangular and then go to spherical. But nowadays, a lot of computer programs are available, they can do it for you. So you just know things. At least sometime you have to do stuff in some place, so you know at least the background, what's going on there. And we just wrote these things. We're gonna say is x equals to rho sine phi, then cos theta, then y equals to rho, z equals to rho. I told you rho is a common. Then sine phi cos theta. Here is sine phi sine theta. Here is cos. Okay. If you want to convert other way around from this system to other system, you can also. You are basically right now doing this. The red line. This is, I'm just writing about the red line, what I'm just doing right now. The other way, if you want to do other way around, you're going to be saying, you know what, I want the spherical from rectangular. You're going to be writing like this. Or you can just say tangent theta equals to y over rho, y over rho, or y over, you can call, you can write this. And sorry, this one not to C is going to be C. You can also elaborate this one, take the theta, leave it here, and then bring the tangent on the other side. I told you can write like this on your calculator, and sometime you can write. Nothing is changed. The way you calculate is not going to change. You just you writing arc cosine, right? Going to be writing like this, z over. So basically inverse of cos. You see here we don't have only tangent here. We don't have a tangent here. We also have x, and that's my phi. So you can say here, if you seeing from the top, and you seeing from the top, here you don't talk about this phi, you only look at theta here and theta here. So really, if you see from the top, cylindrical and spherical coordinates are same. If you see from the top, cylindrical and spherical coordinate are same. So really, it's not making any difference. But when you see from this side, or if you're seeing from this side, then this phi is going to be playing role. So you see, theta formula is pretty much similar, only the phi adding in a spherical coordinate, which is a new addition. Okay. So that's pretty much what we have it today, guys. If you guys have any question, you can stay here. If not, then probably I'm gonna talk to you next week for some other new topic, and we're gonna starting some sort of vector integration in calculus.
Thank you.
Thanks. See you.
Hello.
Yes.
Hi. So I just had a question about the understanding calculus assignment in a Blackboard.
Mm-hmm.
So when I opened the doc, it seemed to be formatted kind of weird. Like there's a question where it says identify the shape of the 3D surface, and there's not really anything there.
No,
I'm not sure.
that's a complete question. So, some other student asking me the same thing. They are actually asking you identify the shape of 3D curve. So you have to give the names from the book. There is no, I mean, nothing is missing is a complete question. You're talking about the one of the assignment called understanding of calculus something, right?
Yeah.
Yeah, that's a complete question, just so you know.
Well, are there supposed to be graphs there, or no? It's just the.
No, no
All right.
graph. Yeah.
So it's just identifying different shapes and writing them down.
Yeah, just like name of the shapes. Yeah.
All right, cool.
Yeah.
Thank you.
No problem.